So in chapter 4, from 4 or 5 on at least, the beginning of chapter 4 had to do with multiplication of polynomials and adding and subtracting. What did we talk about in 4.5, 4.6, in that area, and 4.7 also, actually. 4.7 also had this idea. 4.5 and 4.6 specifically, we started to do what? What's the word? Factoring. Okay, that's what 4.5 and 4.6 are all about. What types of factoring did we go through? There's a lot you need to know for this, okay? Think about this, a bunch of different types. There were special rules and stuff along the way. Okay, so generally, good, we started with polynomial factoring. And what specific cases? What specific cases of polynomial factoring? What are like the special cases that we looked at? Or certain circumstances? All right, the difference of squares is one of them. Okay, the difference of squares. What else? And we'll take a look at an example, one of these at least, or a few of these. What else? What's that? AC method. All right, that's when A is not equal 1, if you recall. All right, so the leading coefficient does not equal 1. That's when we use this rule. Like 2x squared or 6x squared for those. What else? What else? What else? Not squares, but cubes. Sum and difference of cubes. Which I definitely want to go through an example of today, because I haven't even quizzed you on that topic actually yet. It's the only one I think I've hit. There was another one that is kind of important, but kind of not. It's the square of a sum, or square of a difference, where something like your answer becomes x plus 5, x plus 5, when you factor it, and you get the quantity x plus 5 squared. Those were certain cases, and we called that the square of a sum or difference. Those come about when the first term and the third term are perfect squares. We bring them down, multiply them, see if double that gives you the middle term. That was that example. I'm trying to think of anything else. I mean, obviously GCF, right? For all these. So normal factoring, always take out a greatest common factor first. But I don't think we did anything else as far as factoring. Now, how do we apply this idea? We'll look at examples when we get there. How do we apply this idea to 4.7? 4.7 was solving polynomial equations. How do we apply the idea of factoring? So we have to think about what you're learning. The idea of factoring, how did that get applied to solving polynomial equations?
Whatever number that fit in the equation equals 0.
Very good. To solve for the equation's roots or solutions. So for polynomial equations, if you recall, we had some steps that were simple. The steps were first to factor. Well, actually, the first step was to set equal to 0. So move everything over to one side to set it equal to 0. Then factor it. Then think about the zero product property. If you have like 5 factors multiplying each other and equals 0, well, any of them could be 0. So as a result, you set all factors, or set each factor, we should say, equal to 0. And then solve. Okay, so you might solve, if you have 7 factors, how many answers are you going to have? 7. If you have 3 factors, you have 3 answers. And usually, in these cases, it will always be true, but later on in the year it won't. But usually, the amount of factors is equal to the degree of the polynomial. So if it's x to the 4th power, you'll probably get 4 factors, and you'll get 4 solutions. Now, in this section, we're going to see that all those solutions are real. But if we go back, and if we look at more difficult stuff later in the year, we're going to see that some of them are imaginary and not real. Okay? So jot down on the side that the degree of the polynomial is usually equal to the number of solutions. Okay? In our case, for that chapter, it always is. But sometimes it's not. So we take that idea of polynomial equations from section 4.7 and we continue with that into 4.8. How did that apply to 4.8? How did 4.7 apply to 4.8? 4.8 was word problems, by the way. How did 4.8, or how was 4.8 related to 4.7? Luca?
4.8 essentially just using 4.7 in terms of the equations.
Yeah, so in section 4.8, what we end up doing, section 4.8 is we end up factoring, solving, that's an R. Come on, there we go. Solving and applying. So for these problems, what we have to do is you have to think about the fact that when you get an equation from a word problem, you get solutions, but then you need to apply those solutions. What do I mean by applying? Like for example, you're trying to figure out the length of the wall in a room that you've designed. And as results, you get x equals 7 and x equals -2. What do you do with those answers? How do you apply them? Yeah, you can't have like -2 meters as a length for a wall length. So you take your answer and you apply it to what you need. Now, if that also gave you x, but the wall was defined as x plus 7, and your answer was 5, then you take the 5 plus 7, you get 12. So apply that answer to the word problem. So setting it up. You can definitely expect to have a geometry problem for word problems, just to give you a little heads up. You could also expect something where, remember I talked about relationships between numbers, like 3 consecutive integers, have a product of this and a sum of this. Find out one of those integers. So some sort of a problem where you're given some random numbers that you need to determine. Let's see. You could also expect something, remember we did with word problems where you're looking for the time it takes for an object to land after it's launched, and I gave you the equation for the height function. So the height function would say like h of t equals, I think it was -4.9 t squared plus v0t. We did like 1 or 2 of those examples where you're given a function, you're told, determine the time it takes to get to a height of 25 meters. Or determine the time it takes for the object to be launched and come back to the ground level. In those problems, you're given the function for the height. So it's either -4.9 t squared plus VOT, or -32, or -16 t squared plus VOT. Depending on whether it's in meters or in feet, you use one of those equations. You don't need to memorize those equations, but you do need to be able to use them if they're given. Okay, so we can do an example, one of those. And then 4.9, what was 4.9 about? Paul? Good. Polynomial inequalities, yeah. Good. Polynomial inequalities. And for these, we need to remember that the solutions were really called the critical points. Okay, remind yourself if you need to that the solutions to these inequalities, when you make them when you solve them like an equation, those answers you get are called critical points. And then you take the critical points on a number line, and you perform a number line test, and then you shade the appropriate regions. Okay, but prior to that, doing this part right here, you solve it the same way you would solve a polynomial equation. You would factor it, you get it equal to 0 or greater than or less than 0, whatever it is. You would factor it, you would solve each of those factors individually set equal to 0, and those become what are called the critical points. You take the critical points, put them on the number line, test those regions, and then shade the appropriate regions. From the shaded regions, you can write your solution set. last section we did, 5.1 and 5.2, what was that about? Yeah, just rules of exponents. So for rules of exponents, definitely be able to expect things, multiple choice for those. Okay? I'll give you a heads up already. That'll definitely be multiple choice. Okay? All right. Let's do some examples. What would you like to start with? Suggest something, please. Nina.
The one about like the rockets and stuff.
All right, so let's say the following. You can either write it down or listen, whatever you like. I'm not going to write the whole word down. Let's say an object is launched from the ground with an initial velocity of 10 meters per second. Determine the time it takes to reach a cliff that is 60 feet above ground level. 60 meters above ground level. Now, it might go past the cliff, it might go further up, we don't know where it's going to land, it doesn't really matter. We're trying to figure out when it gets to 60 meters at that cliff height. Okay? Now, using the following equation, how would you go about this? And this one is going to be tough because it's going to be really tough to factor. It's probably not going to be factorable, but I want to approach. Give me the approach you would use when we get to the factoring part I'll discuss. Luca.
We plug in the velocity as 10, so it would become negative 49t squared plus 10t, and then you set h of t equal to 0.
And then you said h of t what?
Equals 0.
Equal to 0. Why do you set it equal to 0?
So you can factor it.
Okay. Before you set it equal to 0, though, you have to do something else. Mike?
Just asking a question.
Yeah.
Is it 4.9 t squared for feet meters?
For meters per second is 4.9. For feet per second would be 16.
Oh,
Check the notes for 4.8, I think, that we did this in. You want to correct yourself?
You just set h of t equal to 60 and then you go over.
Yeah, what's the goal? The goal is to find out when this projectile reaches 60 meters. So when it's at 60 meters, what's the height? The height is 60 when it's at 60 meters. Think about it. Here's the projectile. Make believe this is the ground. It gets launched from the ground. Right now it's at 0. 10, 20, 30, 40, 50, 60, maybe up here. So you're trying to figure out how much time it takes to reach 60 meters in height. So set height equal to 60 meters. And then if I want to solve this, as Luca mentioned, we need to get 0 on one side, so move it over. Now, what I would recommend is you multiply everything by -1 before you try to factor. Here it's not going to work, but I'll explain something in a minute. Okay, so you make it look like that. Now, you could try to factor this, but that would be really, really messy. Factor this one right here. Okay, I'm going to make one on the test such that you can either factor or take out a common factor. For example, what if I told you instead of -10, or instead of 10 meters per second as the initial velocity, what if I told you the initial velocity was 9.8? And instead of a height of 60, I'm picking numbers that work now so you can see what I'm saying. Instead of a height of 60, let's say it's a height of 19.6 meters. Now, if those were the numbers instead, So if you changed all these numbers around, I should have picked them in the beginning. What could you do? What could you try to do to make this easier on us, Ben? Everything's divisible by 4.9. That's what Ben was realizing. I was trying to think of multiples of 4.9. So factor out 4.9 and eventually we'll divide by it, yes. Okay, and I don't even think that could be factored still, can it? Of course not. Why would I pick something that works? So instead of 19.6, you would want to use something like 14.7. I'd make that a 3. Would that work now? No, that wouldn't even work still. No, but you need to get a positive 3, that's what I'm saying. See what I mean here? If it were negative 3, it would work. All right, either way, do you get the idea of what you're trying to do? Okay, so when you solve these kinds of problems, when you're trying to find time, you're looking for the unknown independent variable t, you're given the height, so you plug in the height of 60, you plug in whatever the initial velocity is, you then can factor out whatever your GCF is, and then factor the remaining part. Remember, the 4.9 does not matter because there's no variable next to it. So you could simply divide by 4.9, as Ben said a minute ago, on both sides like that, and it drops off because this is still 0 now. And you would get 0 equals t squared minus 2t plus whatever this was, say 3 or 4. And then you could factor that and solve for time. Now, you're going to get 2 answers for time. And I don't know what they are for this problem. Okay, but let's say you get time equals 3 and time equals 5. What is the significance of the 2 answers? What is the significance of the 2 answers? Think again, ready? Here's 60 meters. Here's the rocket. Goes like this. Right? That's what's going to happen. So tell me the significance of time equals 3 and time equals 5 as your 2 answers there. Right?
I think that one of them might be before it passes.
Good, like here. Yep. And the other?
The second time it passes.
Yeah. So think about it. An object, a projectile, will pass a given height how many times? Twice. Unless it just makes it there, right? And it hits the peak at the very top. It comes back down. But if that were to happen, you get a double root. You get t equals 4, t equals 4. And then you know at 4 seconds it hits the top, and it turns around. But if you get something where these are different answers, the lower one is on the way up, the larger one is on the way back down. Does that make sense logically why you're getting 2 answers? So if the question like we posed in class was, how much time occurs between when the object passes 60 on the way up and on the way down, what would you do to find the time duration of this little path right here? How would you determine the time it takes for it to go, ready, from right here to right here? How much time is that?
The difference in the times
So in this case,
is 2.
it's 2. Again, it takes 3 seconds to get here, but it takes a total of 5 seconds to do this. So this is 3 seconds, this is 2 seconds to make it up to 5 seconds. Does that make sense? Okay, the idea of the 2 times and what they mean significantly? How would you determine the time it takes for this object to come back around and reach the ground? Set the height equal to, you did it at the beginning, accidentally.
0.
Yeah, set the height equal to 0. Right? If I want to know how much time does it take for this projectile to come back around and hit the ground, what's the height of the projectile when it hits the ground? It's 0. So you set this equal to 0, you'll get 2 answers. So let's say the initial velocity was 10 again, or 9.8, let's use. Oh, I just said 9.8, I wrote 10. If you wanted to solve this, I set the height equal to 0, not 60. This is no longer 60 over here, this is a 0 now. And as a result, how could I easily solve this? There's an easy way to solve this. Please, don't factor. Don't go create, you're going to factor, but don't factor the traditional way. You have a question or you have an answer? Give me a sec. I know. You gave the answer to the last one. How would I go about solving this?
Negative 4.9.
Okay, that's one way. That's one thing you have to factor out. So factor out negative 4.9. Paul, what else? The t would come out of both also. So here, I'd like you to factor out negative 4.9t, leaving behind t minus 2. Again, if you factorize something out, divide both terms by it. Dividing the 9.8 by negative 4.9 is what gives you negative 2. The t divided by t gets dropped off, so it's just negative 2 there. So how would I solve this now? How do I solve something that doesn't have two binomial factors? Here's a binomial factor, but here's a monomial factor. How would I go about solving this? I've definitely got two factors still. I've got two factors.
Would it be for the monomial 0?
Yeah, very good. Remember, and I mentioned this to you, I told you to write it down. Whenever you factor out a variable as a GCF, the answer becomes 0 because if you think about it, here's what you get. You set each factor equal to 0 like we always state. Then you go ahead and you solve. Divide both sides by negative 4.9. Well, t is still equal to 0 because 0 divided by anything is 0. And then the other answer is 2. Now, what is the significance of 0 as an answer?
0 represents it minus the time exactly when it starts going up. So it's at 0 times before, like when it starts, right?
Yeah, 0 really means the beginning of the problem, or the beginning of the scenario. Well, when the rocket starts, where is it starting from? Ground level, or 0. That's the starting there. So it's saying, when, remember, we're setting height equal to 0. When is the height equal to 0? Well, before the problem starts it is, so that's time equals 0. And then after 2 seconds, when it hits the ground again, that's the other answer right there. Okay, so you're looking really at like the endpoints of the parabola. And you're finding the times. 0 and 2 seconds into it. Okay? Other types of word problems you could expect, again, like I was mentioning, was something like this. Let's say, the product of two numbers is product of two numbers is 35. That's probably too easy because the only two numbers really go into 35 besides 1 and 35, right? The product of two numbers is 32. And one of the numbers is God bless you. And one of the numbers is 8 more than 4 times the other number. And one of the numbers is 8 more than 4 times the other number. Product of two numbers is 32, and one of the numbers is 8 more than 4 times the other number. Determine those numbers. And I might specify integer, I might say determine those whole numbers. So if I say integer, what should you do to any decimal answer?
Multiply it by 10.
If you got a decimal answer, and I said integers, what do you do to it?
Round it up.
No, you don't round it up. You don't multiply by 10.
You make it an integer.
You don't make it an integer. You're going to get 2 answers. So one of them could be,
Oh, you disprove it.
yeah, it's rejected or disproved. You say it's not true. So if the problem says, determine the integers such that blah, 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 and you get 2 answers. One is 4.5 and one is 7. Which answer is it? It's clearly 7 because it said determine the integers, right? So you need to look at your answer and reject any answers that don't fall into the criteria of the problem. So for that question, by the way, it would look like this. What did I say? One of the numbers is 8 more than 4 times the other. Okay, those are your 2 equations there. How would you go about solving this? I'm not going to solve it. I'm just going to discuss. How would you go about solving it? Ben?
Plug the bottom one to the top one.
Very good. Take that definition of x and plug it in right there. Giving you 8 plus 4y times y equals 32. Multiply the y out. Okay? Multiply the y out. Move the 32 over. You'll get 16 and 2. Okay. 16 and 2. And you could have also used process elimination, right? Obviously on the test, it's going to say solve algebraically. So don't sit there and write 4 times 8. Well, that doesn't work. 16 times 2, because it's integers, obviously, there's a limited amount of factors of that. Okay? Let's do an example of inequalities of cubes. Can you check the bell schedule on an E day for third period? What is it?
Well,
Exactly 12?
11.
11.
12.
It's 11 o'clock, though. I think you meant at 12. All right, good. So we have time still. And then you guys know tomorrow. Do you have freshman meeting tomorrow?
Today.
Oh, it's today. Oh, that's today. What period is that? Okay, cool. In the first half of the period, you have something with Mr. Tiozzo today? Do you know? Do you know what you're doing today or no? Okay, wait, do you have it tomorrow then also? Do you have?
No.
Well, Miss Lane was saying that the second half of freshman period is free today, so they wanted you to study with your teachers, so they wanted me to do a study review session with you guys. Is that correct?
First half is with Mr. Tio's, and second half is with like the peer.
Okay, so for the second half of the period, I'm going to be in 403. You understand? So if you want to come for extra help, tomorrow after school also obviously is extra help, but if you want to do some example problems or ask questions or have somewhere to work on problem sets and ask me questions, whatever, just if you want to come by 403 in the second half of your peer leaders today. So let's do a quadratic inequality. All right? So let's say we have x cubed plus 7x squared minus 18x, or let's just say is less than 18x. Let's make it that way. Less than 18x. All right, so here's the problem you've got. It's an inequality, but that doesn't confuse you because you remember, solve it like an equality. Solve it like an equation. So if you solve this like an equation, you have to get what on one side always? 0. So Niall, what's the first step?
Subtract 18x. You get x cubed plus 7x squared minus 18x plus 0.
Very good. Next step after that. Let's go. Let's see who got it quickly. Go ahead, Paul. Good. GCF, always. After that. What's next after that? Ben? Okay, now, do you need AC for this one? What are the factors of 18 that add up to 7? There's nothing here, right? There's a 1 here. So you don't really need AC. You could use AC, but it's the same thing. So what numbers multiply? Go ahead and add up to 7. I would go the other way around. Yeah. It's 9 and 2 for sure, because 9 and 2 can give you 7, right? If they differ, you want this to be positive in the middle, so I want positive 9. You always want the bigger number to be positive if the middle term is positive. All right, so we've done perfectly so far solving this. Now, we find our critical points by solving this like an equation again. So what do the critical points become? And 0. Thank you, Nina. Okay, don't forget x equals 0 out in front. I'm not showing the steps here because they're all binomials that have a 1 in front of the x. So I can just switch the sign and get the answers here. Okay, but these are not my solutions. These are my critical points. I then make myself a little number line. On that number line, I put them in the correct order. I don't care about the spacing. It doesn't need to be drawn to scale. -9, 0, and 2. Obviously not drawn to scale. Now, what do I go about doing at this point? What do I want to do now? There's a certain way to solve these. Paul, what do I do?
Test all the regions.
Good. Test all of the regions. All right. So if I test, where am I going to test them? There's a certain spot I could test them in that makes it easiest.
The factor equation.
In the factored equation, right there at the top. So take a number like 3. Plug a 3 in right here. Isn't that positive when you plug a 3 in? When you plug a 3 in here, isn't that still positive? When you plug a 3 in here, isn't that still positive? Positive times positive is clearly a positive. Then I test the number like 1 in here. Pick the number 1. That makes that positive. A 1 makes that positive, but a 1 makes this negative. So we have a positive times a positive, which is still positive, times a negative makes this region negative. If I test -1, I'm going to have negative here, positive here, negative here. Negative, positive, negative gives me a positive. This is where we need to know our product properties. And then the last one will be negative. Okay? Now, what did this inequality state? It stated, when is the polynomial what? When is the polynomial?
Less than 0.
Right, when is it less than 0? When the numbers are what? Negative. So I shade the negative regions. Open circle. Why is it an open circle and not a closed circle on the critical points? Luca.
Less than, not less than.
Good. It's only less than 0. It doesn't say less than or equal to or greater than or equal to. It just says less than. So I simply shade the negative regions. So a problem like this on your test, it tests you on factoring within testing you on inequalities. You follow what I'm saying? So although you may not, you're definitely going to be given some factoring problems. I'm not going to give you every type of factoring as a factoring problem because some of those types of factoring will occur with inequalities. All right? So it's only going to be like a 4-page test. It's not going to be too long because I'm not going to ask you to factor and then factor again with inequality. Because if you can show me you can factor here, then clearly you know how to factor. Let's look at an example of difference or sum of cubes. First of all, what is a cube? Or perfect cube, I should say. Give me an example of a perfect cube. 8. Why? Because it's 2 cubed. Another? I saw another hand. Another perfect cube. 64, because it's what? 4 cubed.
27.
Give me a variable that is. 27 works too because it's 3 cubed. Give me a variable. What's a variable that's a perfect cube? X cubed. What else? X to the 6th. X to the any multiple of 3. Because think about it, x to the 12th, that's really x to the 4th times x to the 4th times x to the 4th. So let's look at an example now. All right, let's apply this rule. The rule tells me if I have a cubed plus b cubed, I'm going to make this a plus b. I keep the sign, and then I switch the sign here. A squared, what is the middle term going to be? Anybody remember the middle term? You need to memorize this. Go ahead. Negative what? Not negative b. AB plus b squared. Okay? Now, what about if this was a difference of cubes? What's the only difference? Pun very much intended. It's the only difference.
Is it going to be A minus B and just change the sign?
Yeah, it's just a change of signs. Very good. Okay? So we don't have to worry about memorizing both of them. We write it as one equation mathematically like this. What this tells me is the following, and this is really confusing for some students to pick up on, so just watch what I'm pointing to. When I have a cubed plus, see the plus is on the top here of this plus or minus? It means I use whatever's on the top, which is a plus here and a minus right here. But if I use the minus, which is on the bottom of the sign, I use the minus here and I use the plus because that is on the bottom, 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 top, top, top. So you're just consistent with the portion of the multiple arithmetic sign. What is the term for that? Anybody know? I don't even know. It would be a variable arithmetic sign, but either way, if you use the top, stick with the top. If you use the bottom, stick with the bottom, or memorize both separately. So let's see an example. What if you had 27x to the 6th plus 8? How do I know I can use one of these rules? I'm going to only show this. How do I know I can use one of these rules?
27 and 8 are both perfect cubes.
27 and 8 are perfect cubes, and so is what else? Something else has to be.
X is X.
X to the 6th is also. How would I write this so that I see it as cubes? Like 8 is definitely 2 cubed, right? So I can write that. What would this first one be cubed? What's the cube root of 27? 3. And then what cubed gives me x to the 6th? X squared. And think about it. Use your rules of exponents. This is where your rules come into play. X squared to the 3rd is a power to a power. When you have a power to a power, you're really multiplying these, which gives you the 6. 3 cubed gives you the 27. So isn't this true, what we just wrote? Therefore, this is A, and this is B. You are really writing this in A cubed plus B cubed form. So A is 3x squared. B is 2. So literally take that and plug it in to that factored form on the top right over there. So take this value of A and plug it in here, here, and here. Take this value, which is B, and plug it in here, here, and here. So this becomes, when factored, okay, this entire thing up here, when factored, becomes A, which is 3x squared, plus B, which is 2, times A squared, so the quantity 3x squared squared, that's A squared, minus A times B plus B squared. So I'm literally identifying A as whatever this is, identifying B as whatever this is, taking those values of A and B and plugging it into that memorized formula I wrote down. And then at this point, I can just make this look pretty. All right? I can just make this look nicer at this point. That's all I have to do. 3x squared plus 2. What's 3x squared quantity squared going to give me? What does this simplify to? 9x to the 4th. Now this is just going to be minus 6x squared plus 4. So that is the factored form of that original we started with, which was 27, 8x to the 6th plus 8. Factors into this. All right? Just a technique to practice for when you're going to use it later on. Okay, we're not really seeing any applications of this right now. I'll tell you that for sure. Okay, the reason being is that to solve this, you got to use a algebraic formula, and I think your answers would be imaginary. Yes, they would definitely be imaginary. Okay, we haven't even gotten to that yet. So just a technique to practice factoring. Difference of squares, quickly, because we have difference of squares. Let's say we had 4x squared minus 25y to the 10th. Factor, please. We know it always factors into a plus b, a minus b, but we could start rewriting this, right? Remember, think about rewriting this as a squared minus b squared. What would go in for the first term? What makes 4x squared? What quantity squared gives me 4x squared? 2x. How do you know that? We'll go back and do it. Take the square root of these individually. Square root of 4 is 2. Square root of x squared is x. How about over here? What squared will give me 25y to the 10th, right? 5y to the 5th. I know that is true because I'm going to distribute this 2 right here. That'll make that 25. That'll make that y to the 10th. So this is a now, right here. So 2x goes here and 2x goes here. B is 5y to the 5th. That goes here and that goes here. And then other terms become plus and minus. These are binomial conjugates. That's the word we use to describe them. So the examples we didn't get to, like AC method and those other ones, practice please tonight. Do your problem set. Okay, come see me if you want during the end of 5th today. And then tomorrow after school if you need. Don't forget tomorrow to turn in your problem set by the end of the day. We'll do by 3 o'clock, but I don't want you to be like doing it during the school day. If you're doing another class, I'm going to give you a 0. I'm serious. Okay, so don't be doing your work in other classes. If you need lunch, though, just to put it together with your partner and then turn it in to me, just get it to me by the end of the school day. Okay, hard copy or Dropbox.